All right. So here is our example of hypothesis testing with p-values. Step one, as you recall, is make a hypothesis. So when you're making a hypothesis, you need to first set your null hypothesis, which is that the observations or the statistic that you're looking at is a result purely of chance, or it's in line with some known value or known parameter of data. Which means then that your alternate hypothesis is that there is something going on in the data that is not random, or there's something going on that makes the value of the observations different from what we know about the observations of the data, with some random variation thrown in that comes from sampling error, that comes from bias and variability. So when you're setting up your null hypothesis, just remember that that is the boring hypothesis, and your alternate hypothesis is the interesting one that allows you to start investigating what are the systematic factors that are producing these values, or what are the systematic values that are giving you an effect in your data, or that are making your observations different from what is known. So the next step in making a hypothesis is setting your confidence level. We've covered this extensively, especially if you need some extra help. There are 2 mini lectures on confidence intervals, constructing them and interpreting them. So we're going to assume for this example that I'm setting a confidence level of 95%, which means that my alpha is 0.05. The next thing we have to consider is whether or not we are having hypothesis testing that is one-tailed or two-tailed. And what you really need to remember is that when we're talking about one-tailed or two-tailed, we are talking about the alternate hypothesis. Regardless of whether you choose a one-tailed or a two-tailed test, your null hypothesis will remain the same. So I will give you an example. Let's say that we have a null hypothesis that we expect that 50% of New Yorkers in our sample enjoy chocolate or report enjoying chocolate. Now that 50% represents either some random process where, there's a binomial process where half of people enjoy chocolate and half of them don't. Or I could be pulling that number from known literature or subject matter expertise on the eating habits of New Yorkers on chocolate. So that null hypothesis is going to remain the same. Now, my alternate hypothesis can either be that if I reject my null, that 50% of New Yorkers in my sample enjoy chocolate, I can either say, well, if that's not true, then I would expect more than 50% of New Yorkers to enjoy chocolate. Or in a separate alternate hypothesis, I could say, I expect then less than 50% of New Yorkers will enjoy chocolate. And choosing whether or not, your one-tailed hypothesis is more or less than the value you're testing is really going to depend on the question that you're asking and the knowledge that you have about it. So with one-tailed, you have 2 alternate hypotheses. Either you expect the values to be higher than what was in the null hypothesis, or you expect them to be lower than the null hypothesis, which I'm calling that 50% I'm calling a preset value. So when you're working with one-tailed hypothesis, you need to specify whether or not, if you reject the null hypothesis, that you are expecting then that the value will be higher or lower than whatever that preset value was that you had in your null hypothesis. If you have a two-tailed test, then your alternate hypothesis is that the values, the observations that you're looking at, the test statistic is either higher or lower than the other, but you're not specifying which. You just know that it's different than the null hypothesis. So one way to represent this mathematically would be to use our math language. And for a one-sided test, you would say that what is in our data, we're expecting this sample statistic to be equal to some preset value. So this is New Yorkers' enjoyment of chocolate in our sample will be equal to 50%. The alternate hypothesis then could be that the New Yorkers in our sample enjoy chocolate more than 50%. right? This preset value here this is imagine 50s in here, and this is whatever value that we have from our sample of New Yorkers and their chocolate eating habits. Or you could have the null hypothesis remains the same, that 50% of New Yorkers enjoy chocolate, but then you could say, if we reject this hypothesis, then we would expect that less than 50% of New Yorkers enjoy chocolate. Okay, and with a two-sided test, what we're actually saying is same null hypothesis, 50% of New Yorkers enjoy chocolate. The alternate hypothesis is that 50% of New Yorkers do not enjoy chocolate, or that number is not 50%, but we're not sure if it's higher or lower. So with that, we're going to work on an example where our hypothesis is that our test statistic is equal to 5. And so what this actually means, to give you some context, is that my hypothesis is that UAlbany students drink 5 alcoholic beverages a week. My alternate hypothesis is that my test statistic is not equal to 5, and that is that UAlbany students drink more or less than 5 alcoholic beverages a week. And I'd like you to pause for a moment and to think about, is this a one-tailed or a two-tailed test? If you said that it was a two-tailed test because we don't care and we're not specifying whether our statistic is more or less than 5, we're saying it can be either more or less, you're correct. And so what's actually going to go on here with testing our hypothesis is that we're going to look at our normal curve, we're going to look at this density curve, and we're going to evaluate where our statistic lies in this known distribution. Okay? So what we're actually saying is that if our z-score, which is based on our test statistic, lies within this white area, we are not going to reject our null hypothesis. We are going to fail to reject it. We don't have enough evidence to say that UAlbany students drink more or less than 5 alcoholic beverages a week. However, if our p-values, which we calculate from our z-scores, are in this yellow region, or they're in this yellow region, what that means is that we're in the rejection zone. And nobody likes rejection except for scientists. So being in this yellow area is actually kind of exciting because it means that you get to reject your null hypothesis and you're looking at your alternate hypothesis. So you remember that these yellow areas and the p-values are actually talking about probability. So the area under this curve, right, that's next to this line, is the area which equates to the probability related to our hypothesis, affirming our hypothesis or rejecting our hypothesis. And the same is true for over here. Now, just to play devil's advocate and to give you all a little bit of more in-depth understanding about hypothesis testing in the two-tailed and one-tailed settings, we could have set up an alternate hypothesis that UAlbany students drink more than 5 alcoholic beverages a week. And we call this a one-tailed right test, because what we're doing is we're saying more than 5 alcoholic beverages a week. We're looking at this rejection zone, this yellow shaded area that's to the right. So if our z-scores that we calculate our p-values from are over here, then we're going to reject our null hypothesis. If they're in this area, anywhere in this area, then we fail to reject. So thinking about it, you can see why there is a little bit of risk, and you should be careful when choosing what kind of test you're doing. Because if you have a one-tailed right test where your alternate hypothesis is that, well, if students don't drink 5 alcoholic drinks a week, then they drink more than 5, you could actually miss this really important effect over here that students, if they don't drink 5, are actually drinking less than 5. And the same is true for our other example of the null hypothesis that UAlbany students drink fewer than 5 alcoholic beverages a week, which would be a one-tailed left test. So we're looking at the area over here, our z-score, and our p-value is looking at the area under the curve to the left. And what we're saying is that if our p-value is over here, if it's this area of the curve, then we would reject our null hypothesis that UAlbany students drink 5 alcoholic drinks a week, and we would say that UAlbany students drink fewer than 5. However, that same caveat also applies that you need to be careful when choosing one-tailed left or right tests, because this area over here, all of this, if your observation falls in here, you fail to reject your null hypothesis. So what that means is that if students are actually drinking a lot more than 5, you won't be able to tell that with your hypothesis test, because you're looking at this whole area as evidence to support your null hypothesis, where this is the evidence to reject your null hypothesis. All right, so enough of that. Step 2 is to gather your data. If you double-click on the embedded Excel sheet, you should have access to the data, which is a simple random sample of 100 UAlbany students who report the number of drinks they have per week. So step 3 is then to find the p-value, and we're going to go over this, what I'm going to call the hard way or the table way first, just so that you kind of understand what's going on, where these p-values are coming from, and how to use the tables, and then I'm going to show you an Excel shortcut. So in order to find the p-value, the hard way or the Excel way, the first thing you need to do is to calculate the z-value. And you all should be familiar with this formula where the z-value is our test statistic, in this case x bar, our sample mean, minus the population parameter or the hypothesized value. So this would be the mean of our sample, and this would be 5 because that's our hypothesized value. And then you would divide it by the standard deviation of the population divided by the square root of n. Now, we don't actually know the standard deviation of the population, so what we're going to do is to substitute in the standard deviation of our sample. All right, so let's do this. We're going to go into Excel, and I think this is about the 20th time that I've done this because we've had some recording issues here that hopefully will not happen again. But let's walk through this. So our z-value is really just going to be, in this case, our sample mean, or the mean of our sample, minus our hypothesized value, divided by the standard deviation, which is divided by the square root of the number of our observations. All right, so that means that we need 4 things. We need our sample mean, we need the hypothesized value, we need our standard deviation, and we need the square root of our observations. So our sample mean we can get very easily by using our Excel command average and selecting our data. Our hypothesized value is 5. I gave that in the null hypothesis that UAlbany students drink 5 alcoholic beverages a week. And the standard deviation, we can just use standard deviation dot s. Now here, I'm using .s instead of .p because we were working with samples instead of populations. And to this point, we've used standard deviation .p to calculate the standard deviation of our populations. The difference between standard deviation .p and .s is that in calculating the standard deviation, the population .p uses the total number of observations, while standard deviation .s actually they use degrees of freedom instead. And degrees of freedom is the total number of observations minus 1. And the reason that they do that is related to how we use samples to generate inferences about populations. I'm not going to make you learn the proof. Just trust me that you need to use standard deviation .s. Okay, so we're going to select our data. And then we need the square root of our observations. I've told you that this is 100 students, UAlbany students, and their drinking habits. So I'm going to do the square root of 100. So then to calculate our z-value or our z-score, it's the same thing. All I need to do is take the sample mean minus the hypothesized value divided by the standard deviation, which is divided by the square root of the observations. So we get a z-score of 1.478, and I want you to remember that we can round up in this case to 1.5. One of the drawbacks of the table is that you can't get super precise with your z-scores. You need to generally, with tables, only go out to the 10th place, which can be problematic. But let's go to our tables. And you'll see actually in the PowerPoint presentation we have a link right here that will take you to the z-score table. So what we need to do is do two things. The first thing we need to do is to understand which test we're using, if it's one-tailed left, if it's one-tailed right, or if it's two-tailed. If it's one-tailed to the left, we're talking about hypotheses in general where we're hypothesizing that the value will be less than. Okay, so this would be students are drinking less than 5 drinks a week, excuse me. And you can see that in this picture up here because this is telling you that the p-value, which is reported in this table, is this gray area over here to the left of z. So this value down here is the area under the curve right here. So this would be for one-tailed left hypotheses. Now, one-tailed right hypotheses, you would use this table down here, and you'll see it tells you right here that the p-values that you have in this table are actually this entire gray shaded area. Right? But the problem is for one-tailed right hypotheses, for example, if we're saying that students are drinking more than 5 drinks a week, we want this white area right here. So the way that we get this white area right here from these p-values is actually to subtract the p-value given in this table, which again is this gray area, from 1. And that gives us the value over here that we're looking for, the probability that is the area under this curve. So with two-sided tests, we actually run into a little bit of a conundrum because we've got the left and we've got the right. So the way that you would get a two-sided test is that you would actually multiply the p-value by 2 so that you get this area right here and you also get this area over here. All right, so with our example, it is a two-sided test. We have our z-score, which is 1.5. What we're going to do is to find 1.5 under the z part of this table, so that's right here. And then we need to find our alpha level on the top of the table. And our alpha level is 0.05. So that's right here. And we would go down and we'd find where these meet, which gives us a value of 0.9394. So you should write that down. So we're going to go back to our Excel. And we remember, okay, the p-value from table is 0.9394, okay, which means that the p-value that's associated with the right hand or the right tail is actually equal to 1 minus 0.9394, okay, which gives us a value of 0.0606. Now the key thing to remember here is that we need to multiply that by 2 because we're doing a two-tailed test. So p-value two-tailed is just going to be this value multiplied by 2. And that's 0.1212. So if we go back to our data here, we know the next step is to compare our p-value to alpha to figure out whether or not we're going to reject or fail to reject our null hypothesis. And what we find is that our p-value is 0.1212 and our alpha level is 0.05, So our p-value is greater than alpha, which means we don't have the evidence that we need in order to reject our null hypothesis. Therefore, we fail to reject our null hypothesis. Now, just for the sake of going through the motions with a one-sided or two-sided, or excuse me, with a one-sided left or a one-sided right test, what we're going to do is we're going to go back to our table, and I'm going to ask the question, if we were doing a hypothesis where we were saying if we reject the null, our alternate is that students drink less than 5 drinks a week. What we would do is we'd still be using our same z-score, which was 1.5, so that's exactly the same. And then we would go here and we would find our value of alpha, which is 0.05, and we would find where that is, and that gives us a value of 0.0606. Oh wow, isn't that strange? That number sounds familiar. So our p-value for a one-tailed left, which is less drinking, is actually 0.0606, which is the same p-value that we got for our right-tailed test. Okay, so then we would go back and we'd say our p-value is 0.0606. We would look at our alpha level. We would still reject or fail to reject our null hypothesis because 0.0606 is greater than 0.05. But we'd actually be closer. And if we had in fact set our alpha level, for example, to 0.10, at this point, if we had a one-tailed left hypothesis, we would reject our null hypothesis in favor of our alternate hypothesis. Now, what happens if we were doing a right-tailed t-test, which is saying that students are drinking more than 5 drinks a week? Well, we would use the same z-score. So we're using this table right here that we need to subtract our p-value from 1. We would go down here to 1.5 and we would look at our alpha level, and we would go all the way down here, 0.9394, and I would go over and I would subtract just like we did before, equals 1 minus 0.9394. So you'll actually find that the p-value associated with a left or right test is exactly the same. All that's different is the interpretation. All right. So that ends our mini lecture example on using p-values for hypothesis testing, and this will be the focus of your homework, which is due next week. So as always, if you have any questions, please feel free to contact me, and I hope you all have a good holiday, and I will see you next week.